All right, so big ideas from a couple weeks ago. What is a fraction? The two ideas I'm going to use today are equal parts of a whole and comparison through division. And so then based on that, we're going to take a look at why we have to add the way we do, and then subtract, and then we'll look at multiply, and then we'll look at divide. So first, addition. And let's pick on, how about 1/2 plus 1/6. So if I want to come up with the answer for that and be able to be convinced that that's going to be the right answer, then I have to include one of these ideas about fractions up there. And I have to include, what does it mean to add? Add's pretty straightforward. Add is just combine and count. And first we'll try this with just hand sketching our own fractions, and then we'll try it with some toys. Okay. So draw your best picture of a half. And I find I do better with square-ish type things. So this is my best artistic rendering of a half today. Now, I'm going to go with the equal parts of a whole for what it means to be a fraction. So next I want to draw my best sticks with the same size whole. And often with kids, we'll have worksheets where these holes are pre-drawn, pretty close to the same size. And now I got to cut this into sixths somehow. There's lots of ways to do that. I'm just going to make vertical slices on this one to make that happen. And to do that, I'm going to go in half this way and then in thirds that way too. Oh, that was a little messy. All right, erase, try again. That's a little better. And again, there's lots of ways to draw this. This is just one. And I just get to pick one of those. So that's my best rendering of 1/6. And I need to put those together. All right, so there's a half, there's a sixth, equal parts of a whole, combined. So I think I need to put them together in a new picture. Like maybe this is leftover birthday cake. I want to put them all in one pan. What am I going to get? Sometimes it'll all fit in one pan. Sometimes it won't. So let's see, to get them to fit in one pan, oh, I got to do some slicing up to kind of make it fit better. So I think before I do that, I'm going to make them similar. I'm going to take the sixth and I'm going to cut it like the half cake was cut. And I'm going to take the half cake and I'm going to cut it like the sixth was cut. And again, why do you think I bothered to do that? Anybody? So I need equal parts of a whole. And is a half the same size as a sixth? No. So I got to do something to be able to compare them to kind of make them equal parts of a whole. So I had to do some cutting. Is that the only way to do it? Nope. There's lots of ways to do it. In some problems, I'll draw this a different way in a minute. So let's see. My cake is going to be cut up this. And then I'm going to drop the yellow pieces in. 1, 2, 3, 4, 5. It looks like there's 6 of them. 1, 2, 3, 4, 5, 6. Okay, they're all there. And then from the red cake, I got to drop those 2 guys in so they'll fit nicely down here. I combined them. Count them up. How many are there? 6, 7, 8 pieces in there at first glance. So it looks like I have 8 out of 12. Now, that's not the only way to look at this, though. You might have drawn the picture different. And it could be I kind of regroup like this. Now I have 4 equal sized pieces out of 6. So I could regroup and say, oh yeah, but you could also say that's 4, 6. Could I regroup again? Yeah, I could regroup again. Let's see, I'm running out of colors. Let's try a blue highlighter. I could say this right here is a group, and that right there is a group, and that's a group I don't have. So also another answer would be 2/3 here, once we regroup. And those are all great answers. They're all this final result. There's different ways to talk about it there. Bottom line, though, is you have to have a common denominator to add fractions. Otherwise, you can't necessarily put them together in the end. So I'm just going to look at this in a slightly different way with some toys we were playing around with last week. Same problem, 1/2 plus 1/6, but we're going to do it with the pattern blocks. So often with the pattern blocks, we decide that this is going to be one whole. And those of you in the classroom, you might want to grab some of these to play with because we're going to use them a bunch today, unless you're really good at drawing these. We're really good at drawing them. Okay. Yes, come grab some then. So those of you watching along online or in the future, you could grab the pattern shapes from the Math Learning Center. If you're in my Canvas course, you can find that linked in the resources or linked in most of the fraction activities. These are challenging to draw for most of us that aren't good drawers. Make myself a little key here. Got full. Now, we figured out before that those green triangles end up being 1/6 of that whole, and the blue trapezoid ended up being 1/3 of that whole, or the blue rhombus, excuse me, and the red trapezoid ended up being 1/2 of the whole. So then here I want to be able to use these things to show what does 1/6 plus 1/2 look like. So add means combine and count. So let's combine. Let's put 1/6 and 1/2 together in the same whole. So if you have the physical pattern blocks, lay down a hexagon, throw on there a triangle for 1/6, and then throw on there a trapezoid. And I'm going to reorient these a little bit. I'm going to take that right there, stick it there like that. All right. So this is one version of the answer. They happen to fit together nice. Problem, I've combined, but how do I count that? Well, the green plus the red, could I say it's 2 of something? That doesn't quite make sense because fractions have to be equal parts. Are the green and the red equal in size? No. Okay. So that means I have to do something different. One option here would be to replace the red trapezoid with green triangles. All right, because I can't count those and say there's two pieces there because they're not equal. Fractions have to be equal parts. So back here, I'm just going to do a little remodeling and slap that on there for fun. And again, it's more fun with the real ones than the digital ones. So that's another version of my answer. So now at least I can look at and count. So here, right, they're combined, but I can't count them because they're not the same size piece. Now I can count and I can see that there are four pieces. For what? 4, 6. Yeah, 4 out of 6 equal pieces in a whole. So the answer, one answer here is 4, 6, which we found a slightly different way before. This green triangle is pretty much finding a common denominator. What am I saying the common denominator has to be here? It's got to be 6. Yeah. So what I'm saying is here, you can say, well, that's the same as 1/6, and a half we just showed is really 3/6. Oops. Which altogether, when we combine them, is 4/6. So when we're combining fractions, we have to have a common denominator. That's what the picture shows. It also shows us that we only add the numerators, we don't add the denominators. And a common misconception is a lot of people want to add the denominators too. But it turns out most of the time that's not good. Can't do it. Is that the only possible answer here? No, what's another answer besides 4, 6? Can we show that with these shapes? Yeah, what other toy can I throw on there to look at this a little bit different? Yeah, I could put a couple blue ones in there. All right, so let's do that. Go back here. Let's see, I think that's going to involve some rotating. So I could do that there. And so this gives me another possible answer. Oh, yeah, because the blue one's 2/3, or 1/3, excuse me. Another possible answer here is 2/3. So first question, what's the common denominator in this situation? 6. Yeah, we had to use 6 to make this happen. That is the smallest denominator you could possibly get away with here. There is a thing called the lowest common divisor, which is related to the lowest common denominator when we're adding fractions. I could have done it with a higher denominator. Here I ended up with 12ths. That worked okay. But there's no way you can use any smaller number than 6 in the denominator to make this happen. Now, however, we were able to reduce, but that's a whole nother issue. We happen to get lucky in this reduced. You don't always get to reduce. Sometimes things reduce, sometimes they don't. Okay. So I've got 2 different methods here. That should say count. There we go. One where we ended up using the lowest common denominator, one where we did not. And they both work fine. Okay. So important lesson here, because a fraction is an equal part of a whole, and because addition means combine and count, it turns out there's no getting around having common denominators when you add fractions. Gotta happen. That's life. This also, if I do a whole bunch of examples with these, gives me 2 different ways to add fractions without pictures. And hopefully you read about this in the book. So fraction algorithms. We have 2 choices. The most common one is called the LCD algorithm. Lowest or least common denominator. So just with the example of 1/6 and 1/2, or 1/2 and 1/6, either way, somehow I have to be able to look at the denominators and figure out what multiple of those is the smallest one we can get away with? And most people look at that and recognize, oh, 2 goes into 6 3 times with no remainder. So that means 6 must be the lowest common denominator here. And once they make that discovery, they use that 3 there to adjust. In this case, we only need to adjust one fraction. And so this tells me that I can take 1 plus 3, 6. We don't really need to write the denominator more than once anymore, which happens to be 4 6. And we'll try that again with some more complicated denominators. Sometimes 2 divisions need to happen because both fractions need to be adjusted. It just depends. Okay. Versus a second algorithm I call the arrow algorithm. And the arrow algorithm comes from the way, in my first example back here, the way I cut each of these like the other. So if we take that idea to this problem right here, what we do is we say, well, what's happening is we're taking the 6 and we're cutting them in half. 2 times 1 gives me 2 pieces. We're taking the halves and we're cutting them in 6. 6 times 1 is 6 pieces. And we also have to do that with each denominator. 6 times 2 is 12. So we do this cross multiply, slide across the bottom. And that's where in my picture before, I ended up with 2 plus 6, or 8 pieces total out of 12. This just finds a quick denominator. It doesn't worry about it being the lowest one. So my question then is, well, do we have to find the lowest common denominator? Well, clearly not. We just have to find a common denominator. Downside, over here, I have to reduce more. I still had to reduce even with the lowest common denominator. Like, why do I have to find it? There are some times when it is a little bit nicer to have the smallest denominator, which means there's a little less reducing to do later, but there's no guarantee. Do a lot of people have trouble with this here because it's got like 5 steps to it? Yeah. Number one stumbling block in arithmetic. This one has less places to stumble. 2 different ways to do it. Both work with subtraction. Subtraction is just taking away something instead of putting them together. Same idea works. Either you can do the lowest common denominator or you could do the arrow algorithm. Either way, you gotta have a common denominator. All right, so that's an overview of last week, modeling addition of fractions with some toys. That can either be done with toys like that, or sketches that are drawn with squares or circles that work fine too. Questions on addition and subtraction of fractions? Right. So mixed numbers, going with the assumption before that a yellow hexagon is a whole, I have 2.5 wholes, which we write like that. But when we say it, we say 2.5. And it literally is a plus that we just don't write. That's important. Now, also, I could look at this and say, well, I could split each of these hexagons into 2 red trapezoids. Easier to trace than draw myself. And so another way I could view this is there are how many halves up there? 5 of them, right? So I could say that's 5 halves. So again, relationship here is mixed numbers to, what do we call this kind of fraction? Improper. Yeah. And usually if my mom or my grandmother said I was improper, then I was in trouble because I just did something wrong. There's nothing bad about improper fractions. They're actually great. Because if it turns out I need to do calculations, I'd rather calculate with an improper fraction. Oh, oops. But I wouldn't tell somebody, go drive 5/2 miles to get to this place. I would say 2.5 miles, right? So these mixed numbers, we like to say them. They're just two different ways of looking at the same number. One we use in speech more often, the other is better for a calculation. Mixed numbers are not good in calculation. They cause trouble often. Just double check. Remember, when we see that, we read it as 2.5. If I'm going to add these, they need a common denominator. So I would rewrite that as 2/1 plus 1/2. Common denominator here would have to be halves. So I'd multiply top and bottom by 2 there. So that means I have 4/2 plus 1/2, which gives me 5/2. Usually we do a little shortcut thing there. We do something like take this 2 times that 2, and then add it to the number above. And that's where we come up with the 5/2. You're probably familiar with that process before. But this is why we